Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 27, Atmospheres and Oceans. Now that we've taken a look at the surface of the Earth and the interior of the Earth as a primer for studying the other terrestrial planets in our solar system, let's also now look at the atmosphere of the Earth and compare it to the atmospheres of the other terrestrial planets. Along the way, we'll learn a bit more about atmospheres and why some planets and moons have atmospheres and others do not. Let me start with a beautiful image of the Earth's atmosphere. The primary thing that I want you to get from this image of the Earth's atmosphere is how thin the atmosphere is. You'll remember that the radius of the Earth is 6,378 kilometers. Now, the atmosphere doesn't really have an upper edge to it. It just gets thinner and thinner as you go higher and higher. But for contest purposes, they often consider 100 kilometers or 60 miles to be the upper edge of the atmosphere. So think about how thin that is. 100 kilometers thick is our atmosphere compared to the radius of the Earth of 6,378 kilometers. Okay, let's do a learning catalytics question about the Earth's atmosphere. The Earth's atmosphere is primarily made of what gas? Is it carbon dioxide, nitrogen, oxygen, or argon? What gas makes up the majority of the Earth's atmosphere? So go ahead out to Learning Catalytics, answer this question, come back when you're done. Okay, so what did you put for the gas that primarily makes up the Earth's atmosphere? The gas that makes up the Earth's atmosphere, the majority of the Earth's atmosphere, is nitrogen. So the atmosphere is that thin layer of gas that surrounds the Earth, and the composition of the Earth's atmosphere consists of 77% nitrogen, about 21% oxygen. Argon makes up about 0.9%, water vapor is about 0.3%, and carbon dioxide is 0.03% of the atmosphere. So interestingly, nitrogen makes up the majority of the Earth's atmosphere. Many people will select oxygen as being the primary constituent of the Earth's atmosphere, and that's because we always talk about the fact that you and I and animals need oxygen to live. And although we need oxygen to live, and the nitrogen in the atmosphere does us no good, our atmosphere is only a little bit more than 20% oxygen. Now, here on the surface of the Earth, each cubic centimeter of our atmosphere contains about 2.4 times 10 to the 19 molecules. So let's put that in perspective. A cubic centimeter is 1 centimeter by 1 centimeter by 1 centimeter. So this little box that is that big by that big by that big contains 2.4 times 10 to the 19 molecules. 10 to the 12 is a trillion, 10 to the 15 is a quadrillion, 10 to the 18 is a quintillion. So that's 24 quintillion molecules in a little tiny box that is 1 centimeter by 1 centimeter by 1 centimeter. To put that in perspective, throughout most of the Milky Way, there is an average of 1 atom per cubic centimeter. And here on the surface of the Earth, there's 24 quintillion molecules in that same little box. So that's a lot of molecules. That's a lot of atmosphere. And we don't often think of the atmosphere as having any weight to it, but in fact, the weight of the gas, if I take 1 square inch of the Earth's surface, so 1 square inch of the surface going all the way from the surface of the Earth up into space, the weight of all that air pushing down on me is 14.7 pounds. And we call that atmospheric pressure 1 bar or 1 atmosphere, but it's 14.7 pounds per square inch. So that's how much the air above you weighs. 1 square inch of air weighs 14.7 pounds. Now, when we see astronauts in space, I love this image of Bruce McCandless. He is the astronaut that is in the spacesuit there, one of the few times that astronauts were able to float away from the space shuttle untethered. I think the neat things about this photograph are, again, you can see how thin the Earth's atmosphere is, but I also love the image of the astronaut floating above the Earth's atmosphere, realizing that the whole reason the astronaut is wearing a spacesuit is because the astronaut has to carry their atmosphere with them. Without the spacesuit, of course, they would die, and that's because we need our atmosphere to survive. Here's another image of the Earth's atmosphere, again showing you how thin it is with the Hubble Space Telescope in the foreground. The Hubble Space Telescope was launched specifically to get outside of the Earth's atmosphere for two reasons. The first reason, and the primary reason, is the blurring effect of the Earth's atmosphere. When we take images of objects in the night sky, they always look a little blurry from the surface of the Earth. And that's because as the light comes down through our atmosphere, it gets bent back and forth by the molecules in our atmosphere. Hot pockets of air that are rising up are less dense, and cooler pockets of air are more dense. And less dense air bends light less, and more dense air bends light more. So as this light is coming through and it hits hot pockets and cold pockets, the light gets bent back and forth, and that blurs out our images a little bit. In fact, this is what causes the twinkling of the stars. Stars themselves don't naturally twinkle. Stars maintain a constant uniform brightness for, in some cases, millions or billions of years at a time. The twinkling, the rapid changing in brightness that we see from a star, that's caused by the Earth's atmosphere. That is the light from the star coming through the atmosphere, coming into your eye. But as the atmosphere changes, it bends the light out of your eye and the star twinkles off. And then it gets bent back into your eye and the star twinkles on and off and on and off and on and off and on as that light gets bent back and forth. To avoid this, the Hubble Space Telescope was placed in orbit around the Earth. The Hubble Space Telescope is only about 250 miles above the surface of the Earth. It is not very high above the surface, but it is high enough to get outside of most of the Earth's atmosphere and get a clearer view, I should say, of the universe. Okay, as you rise up through the atmosphere, the pressure decreases and the atmosphere gets thinner. Anyone who has climbed a mountain has experienced this. As we go higher and higher, there is less and less air above us pushing down on us, and so the atmospheric pressure decreases as you go higher and higher. Now, as the pressure decreases, that also means that the amount of oxygen decreases, and that's why you have to breathe harder and harder the higher and higher you go. But the atmosphere just keeps getting thinner. There's no upper boundary to it. There's no upper edge where you can say for certain that the atmosphere ends. For contest purposes, the edge of the atmosphere is usually defined to be 100 kilometers, sometimes called the edge of space. But in truth, the atmosphere goes much higher than that. Even hundreds of kilometers above the surface, where the space shuttle orbits and where the International Space Station orbit the Earth, there is still some atmosphere. This is a beautiful image of the space shuttle orbiting around the Earth on the night side of Earth. In this particular instance, the space shuttle was orbiting the Earth tail first. And as the space shuttle, orbiting about 240 kilometers or so above the surface of the Earth, about 240 miles above the surface of the Earth or so, as it's orbiting through the Earth's atmosphere, as that tail plows through the atmosphere, it excites the molecules of gas to glow. And what you see is the very, very thin, tenuous Earth's atmosphere glowing there. Now, in addition to that glow, it also turns out that that air is providing a little bit of air resistance, and it is very, very gently slowing the space shuttle down. We see that today with the International Space Station. This is a plot of the altitude of the International Space Station. So the altitude is given over here in kilometers, and this is the date running down here. And what you can see with the International Space Station is when it is left alone, it is slowly falling from orbit. And the reason it is slowly falling from orbit is because of atmospheric pressure. It is because of that air resistance from passing through the thin atmosphere, even up here at 250 miles or so above the surface. Now, every now and then, they will use the thrusters on the International Space Station or one of the cargo vehicles to boost the orbit of the space station. And then it slowly decays, and they will boost it, and it slowly decays, and they will boost it, and then it slowly decays, and they will boost it. It slowly decays, and they boost it. And then this was a rare instance where they had to lower the altitude of the International Space Station. And then once they had lowered it, then they let the natural decay take over there. If we didn't continuously boost the orbit of the International Space Station, it would fall from orbit in just about 6 months or so. So we are constantly boosting the orbit of the space station to make up for the velocity, the speed that it loses due to wind resistance. Now, this may be an obvious statement, but some planets and some planetary satellites, some moons, have atmospheres and some don't. So what we'd like to understand in this next section of the lecture is why it is that some planets, like Earth and Mars, have atmospheres. So you can see here the very thin atmosphere on Mars. You can even see some layers in the Martian atmosphere. The Martian atmosphere, as we'll find out, is much thinner than the atmosphere on the Earth, but you can still get clouds on Mars. So these are some water vapor clouds that formed in the atmosphere on Mars. Venus, as we've already seen, has an incredibly thick atmosphere, an atmosphere that is so thick that you can't see the surface. In fact, all that we ever see from Earth are the cloud tops on Venus. We never get to see through the clouds down to the surface. We have landed on the surface of Venus, and I showed you a picture like this a little bit earlier in the course. This is taken by one of the Venera probes. This is Venera 13 sitting on the surface of Venus, looking down at the base of the spacecraft and then slowly tilting its view out to the horizon out there. And we'll talk a little bit later on why this view looks the way it does. There are two factors that determine whether a planet can hold on to its atmosphere. And those two factors are gravity and temperature. So gravity is a factor because of escape velocity. The stronger the gravitational pull, the harder it is for molecules to escape. The more massive the planet is, the higher its escape velocity, and that makes it harder for the molecules and atoms to escape. On the other hand, temperature plays a role. The hotter the atmosphere is, the faster the molecules are moving. And if the molecules are moving fast enough and enough of them exceed the escape velocity, then the atmosphere will escape from the planet. So let's go ahead and let's use this gas simulator, which is going to simulate a gas, to look at some of these properties in a little bit more detail. Okay. So you'll remember this gas simulator from earlier. I'm just going to pump in here 1, 2, 3, 4 good pumps of gas in there, and we'll let them equilibrate in there, which means they're just going to share all their energy and they're going to start bouncing around. And once they get to equilibrium here, I'm going to turn up the temperature. And my first learning catalytics question for you is, what will happen to the particles if I increase the temperature? So I want you to think about what's going to happen to the particles in this box if I increase the temperature of the box. Okay, what will happen to the particles if I increase the temperature? All right, so let's go ahead and do that. You'll remember that there's a little slider down here. I can apply heat to the bottom of the box. So hopefully you've had the chance to answer this question in learning catalytics. So let's apply the heat and let's see what happens. So you'll notice the thermometer up here at the top. There's a thermometer up here at the top. So you'll notice it's getting higher and higher. I don't want to go too high here or it'll blow the top off the box. But what you can clearly see happening is as I increase the temperature, the molecules are moving faster and faster. And this is what temperature means. When we talk about the temperature of a gas, when we measure the temperature of a gas, what we're really measuring is how fast the molecules are moving. In this room, for example, as I raise the temperature, the molecules start moving faster and faster. As I cool it off, the molecules start moving slower and slower and slower. Until, in fact, I get down to a temperature of 0 degrees Kelvin, and that's when I've removed all the energy from the molecules that I can. So now you can see that I have significantly cooled off the gas. The molecules are moving significantly slower. All right, I want you to answer this next question then in learning catalytics. What will happen if I take the top off the box? What will happen if I remove the top off the box? So go ahead and answer this question right now. What will happen if I remove the top off the box? All right, let's see what's going to happen here. So if I remove the top off the box right here and I just slide it away, what you will see is that molecules start to escape from the box. And this is the problem that planets have with their atmospheres, that there is no top on the box. There's nothing holding the gas in. So with no top on the box, molecules, if they're moving fast enough, can escape from the box. Now I could cool these molecules off more and more, and you will see they move slower and slower. And as they move slower and slower, you will see that fewer and fewer of them are escaping from the box. Now, one thing that I can't do in this simulator is turn up gravity. If I turned up gravity, you would find that those molecules are held closer down to the surface. And that's simply because the force of gravity pulling on them, the acceleration from gravity is greater. It makes it harder for those molecules to escape the box. Now let's see what happens if I put some light particles in the box. So let me reset this and let me do 1, 2, 3, 4 pumps of the heavy gas. And now let's switch over here and let's do a much lighter gas. This is a much smaller molecule. So let's pump that into the chamber and see what's going to happen to this lighter, smaller molecule. All right, so now I want you to answer this question in Learning Catalytics. How do the light particles compare to the heavy particles? How does the speed in particular of the light particles compare to the speed of the heavy particles? Okay, I think the answer to that question is pretty obvious, but when you look at this gas here, you will see that the light particles are moving significantly faster than the heavy particles. And that's because of their lower mass and through the conservation of momentum. When those particles collide with one another, they share their momentum. But the smaller, lighter particles, when they collide with one another, in order to conserve momentum, which is the product of the multiplication of mass times velocity, when they collide with those heavy particles, because their mass is so low, they need to have a very high velocity to have the same momentum. So let's go ahead and cool this off. And we'll see that even as we cool it off, the smaller red particles are moving faster than the blue particles. Okay, so now I want you to predict what will happen if I remove the top off the box. So this time, what will happen if I remove the top off the box? Particularly, how will the loss of the red molecules, the red atoms, compare to the blue atoms? So go ahead and go out to Learning Catalytics. Again, it's a word cloud. Just type a couple words about this. What will happen if I remove the top off the box? Okay, let me go ahead and take the top off the box and let's see what happens here. And what you will notice, because the red molecules are moving faster than the blue molecules, we tend to lose more of the red molecules than the blue molecules from the box. That is, again, because of their more rapid speed, because of the distribution of energy in this gas, and the conservation of momentum as the particles collide with one another, we end up losing more red than blue particles in the box. Okay, so putting those things together, which of the following planets is likely to have the thickest atmosphere? So I want you to put these two things together, the strength of gravity and the temperature of the planet. Which one will have the thickest atmosphere? A hot planet with weak surface gravity, a hot planet with strong surface gravity, a cold planet with weak surface gravity, or a cold planet with strong surface gravity? So think about this for a second and go ahead and answer the question. Which is likely to have the thickest atmosphere? Okay, let's see what you thought on this one. I would argue from what we just learned is that a cold planet with strong surface gravity is likely to have the thickest atmosphere. That strong surface gravity is going to hold onto an atmosphere, and a cold planet means that the molecules are moving more slowly and they are less likely to escape. So typically, when we see moons and planets with atmospheres, we're usually looking at planets and moons that have strong surface gravity and they have cold temperatures. But that's not always true, and we'll see that in a little while. All right, let's talk about the Earth's atmosphere. The nitrogen and oxygen molecules in our atmosphere are moving at an average speed of about 0.5 kilometer per second. Now, that's pretty impressive. That's 500 meters per second. In the length of time it takes you to say 1/1000, a typical molecule in our atmosphere could travel 1,500 feet or 0.5 kilometer. The problem is that they collide with many more molecules before they can do that. So though they're moving very fast, they can't typically travel long distances like that. They're constantly just bouncing around, hitting off one another. The reason that we can hold on to the nitrogen and oxygen in our atmosphere is that you'll remember that the escape velocity from the Earth is 11.2 kilometers per second. So for these molecules to escape from the Earth, they'd have to be traveling faster than 11.2 kilometers per second. And the average speed of the molecules is much, much less than that. The average speed is only 0.5 kilometer per second. So now I want you to answer this question. The Earth's atmosphere has no appreciable amount of hydrogen and helium. They're the two lightest elements. Why is that? Is it A, the average velocity of the hydrogen and helium atoms is faster than the escape velocity? B, the average velocity of the hydrogen and helium atoms is somewhat less than the escape velocity, but the fastest ones are moving faster than the escape velocity? Or is it C, hydrogen and helium are lost to chemical reactions on the surface? Hydrogen is converted to water, for example. So go ahead and take a few minutes and answer, go to Learning Catalytics and answer this question. Why does the Earth have no hydrogen and helium in its atmosphere? All right, why do you think it is? Well, I have a feeling many students probably answered A on this one, that the average velocity of the hydrogen and helium atoms is faster than the escape velocity. But it turns out that's not true. On Earth, the average velocity of the hydrogen and helium atoms is actually significantly lower than the escape velocity. But some of the atoms, the fastest moving atoms, are moving faster than the escape velocity. So the answer to this one is B. Let's look at how the velocities of atoms are distributed in a gas. It turns out that when we have a gas, not all the atoms are moving at the same speed. Some atoms are moving faster, some are moving slower. You saw that in the simulation. You may not have realized it, but you probably every now and then saw a particle traveling really slowly while others were traveling faster. For every collision, the fast ones will sometimes end up slower and the slower ones will sometimes end up faster. Over time, we can talk about the average velocity of the gas, the average velocity. But there are molecules that are moving slower than that and molecules that are moving faster than that. And we call this distribution of velocities a Maxwell-Boltzmann distribution. Maxwell and Boltzmann were two scientists who studied the statistics of how gases work, and they derived this distribution of velocities. So this is the number of atoms that have a certain speed, and this is the speed. Now, this particular plot is drawn for our moon. And for our moon, the escape velocity is down here at about 2.3 kilometers per second. And this is the distribution of velocities of a particular gas. And you'll see this is the average velocity down here. Again, some are slower than average, some are larger than average. But the Maxwell-Boltzmann distribution always has this long tail going off to high velocities. There's always some atoms that are moving really, really fast. And it's these ones that are moving faster than the escape velocity that are lost to the planet. And once they're lost, they never come back. And what happens is once these are lost, collisions in the gas will bump more molecules faster than this, and they will be lost. And more molecules will be bumped faster than this, and they will be lost. And over time, you can lose the whole atmosphere. So in order for a planet to hold on to an atmosphere, the average velocity has to be significantly less than the escape velocity so that there are hardly any atoms or molecules out here in this tail out here. We want to lose as few atoms or molecules as possible. So let's look at the planets that are, and moons that do have atmospheres and those that don't. and let's look at their escape velocity, and let's look at their temperature. So this is a fairly complicated plot, so let's go over it because it's well worth understanding this plot. In fact, I think it would be well worth your time really understanding what's going on here. So first of all, down here across the bottom is the temperature of the planet in kelvins. So this is 30 kelvins. This is extremely cold. This is 1,000 kelvins. This is really hot. So this is cold and hot. This is the escape velocity from the surface of the planet, but it's not the true escape velocity. It's 1/6 of the escape velocity from the surface of the planet. And typically, if a molecule's average velocity is much less than 1/6 of the escape velocity, you can generally hold on to that gas, whereas if the average velocity is more than 1/6 the escape velocity, you can't hold on to that gas. So let's take a look at some of the planets here. So let's take a look at Earth right here. So here is the Earth. So there's the average temperature of the Earth, right around 200, not quite 300 Kelvin. So that's the average temperature of the Earth. And the Earth's escape velocity is 11.2 kilometers per second. So we divide that by 6. So we get a little bit less than 2 kilometers per second. So that's where the Earth is sitting. These dashed lines show you the 5 most common molecules in atmospheres: hydrogen, helium, water, nitrogen, and carbon dioxide. And you might know that because oxygen and nitrogen have almost the same weight on the periodic table, the dashed line for oxygen is basically the same as the dashed line for nitrogen there. What this shows you is that if the dashed lines are above the planet, they're moving too fast. There are enough molecules moving fast enough that they will escape from the planet. Whereas if the dashed lines for that molecule are below the planet, then the gas will not escape. So these are the planets with strong gravity. These are the planets with weak gravity. These are the cold planets, and these are the hot planets. Remember, when I say hot, that refers to everything over here on the right-hand side of the graph. When I say cold, it refers to everything over here. When I say weak gravity, it's everything across the bottom, and strong gravity is everything across the top. So let's look at the Jovian planets to start with. So you'll remember that Jupiter, Saturn, Uranus, and Neptune, all of them have tremendous atmospheres of hydrogen and helium gas. Why is that? Well, they have atmospheres of hydrogen and helium gas because look at where they are in this chart. They are well above the hydrogen and helium retention line. And they're up there for 2 reasons. First of all, they're very, very cold. But at the same time, they're very, very massive. They have very high escape velocities. And because it is both hard to escape from them and they're cold, they're able to retain hydrogen and helium in their atmospheres. Now, the Earth has a significantly lower escape velocity, and the Earth is somewhat warmer. And what has happened to the Earth is we are on the other side of the hydrogen and helium retention lines, and Earth has lost all of its hydrogen and helium. When you take a helium balloon and you pop a helium balloon and you let that helium into the Earth's atmosphere, over time, all that helium will be lost to Earth, never to be recovered again. Now, Venus is about the same size as Earth. It has about the same escape velocity as the Earth does, but it's significantly hotter than the Earth. But that said, Venus is not hot enough that it has lost a significant amount of its atmosphere. Venus is too hot to hold on to hydrogen and helium, just like the Earth, but it can hold on to water vapor, it can hold on to nitrogen, it can hold on to carbon dioxide. Mars, on the other hand, is a really interesting case here because Mars is cooler than the Earth, but its escape velocity is a lot lower because Mars is a lot less massive. So obviously Mars cannot hold on to hydrogen and helium, but Mars can also not hold on to water vapor. Water vapor will be lost from the Martian atmosphere, and that gives us a hint as to why Mars is the dry planet that it is today, although early in the history of the solar system, its atmosphere was clearly much thicker and much wetter because we see evidence that there used to be liquid water on the surface of Mars. But over time, Mars has lost its water because it wasn't able to hold on to it. That said, Mars is able to hold on to carbon dioxide down here because carbon dioxide is the heaviest of these molecules. You might have noticed by the way that the arrangement of these lines, I should have mentioned this earlier, let me mention it now. The arrangement of these lines is going in molecular weight. H2, 2 hydrogen atoms bound together, has an atomic mass of 2. Helium has an atomic mass of 4. Water, H2O, well, an oxygen atom has a mass of 16, and the 2 hydrogen atoms bound to it give us a total mass of 18 for water. Nitrogen is 2 atoms bound together. They each have an atomic mass of 14. And so because nitrogen is the 7th element on the periodic table, it has 7 protons and 7 neutrons. So its atomic mass is 14. N2 is 2 of those bound together. So its atomic mass is 28. And then finally, carbon dioxide down here at the bottom. An oxygen atom has 8 protons and 8 neutrons. So that gives it an atomic mass of 16. 2 of those is 32. Plus the 12 from carbon is 44. So these lines are arranged in terms of molecular mass. And that's what we saw with that simulator, right? The more mass of the molecule, the slower it moves, the harder it is to escape. So that's why a lot of things like Mars can hold on to nitrogen and oxygen and carbon dioxide, but it can't hold on to water because water is actually one of the lighter molecules in the atmosphere. Okay, and that's also true for ammonia and methane as well. Okay, let's look at some other planets on here. Both the moon and Mercury have no atmosphere, and neither the moon nor Mercury have an atmosphere because their escape velocities are so low and their temperatures are so high that they are pushed below the retention curves for all of the molecules. So the moon and Mercury have no atmospheres at all. When we get to the outer solar system, some of the moons of the outer solar system do have atmospheres. So before we go on to those, let me talk about Pluto way down here. Pluto has a very low escape velocity. And even though it's very, very cold, Pluto does not have a substantial atmosphere because its escape velocity is so low. So the moon and Mercury have no atmosphere. Those bodies did outgas. Material came out of their surfaces. We'll see where atmospheres come from a little bit later on. So they did outgas material, but they have lost that material over time because their temperatures are too high and their surface gravities are too low. And so they have lost all that gas. Pluto is a lot less massive than Mercury. It has a low surface gravity. It has a very, very thin atmosphere because it is so cold. But and the molecules are moving so slowly, but it is a very thin atmosphere. 2 of the moons of the outer solar system, Titan, for example, here, and Triton. Titan has a significant atmosphere, as we will see in a second, made up of carbon dioxide, and that's because it is cold. Even though it is smaller than Mercury and its escape velocity is less than Mercury, it is cold enough that it can retain an atmosphere. So there is the moon with a lack of an atmosphere. We will talk about the consequences of that coming up in our next couple lectures on the geology of the moon. This is the far side of the moon, you might remember. The way you can tell that the moon has no atmosphere is from any photograph that you'll ever see of the moon. You'll see this very sharp edge. If a planet has an atmosphere, you'll usually see a fuzzy edge to it, but it's got this very, very sharp edge on the photograph, and that is the moon. And here is Mercury also with its lack of atmosphere. Just like the moon, Mercury has no atmosphere. All right. I did mention, however, that Titan has an atmosphere. In fact, Titan has an atmosphere that has twice the atmospheric pressure that we have here on Earth. Titan, like Venus, has an atmosphere that is so thick that we cannot see the surface in visible light. Titan's atmosphere is the thickest atmosphere of any moon in our solar system, and it can hold on to a substantial atmosphere, not because it has a very high surface gravity, not because the escape velocity is very high. The escape velocity is quite low, but because it's out here at the edge of the solar system where it is very, very cold. So that is why Titan can retain its atmosphere. And in fact, here's a beautiful picture of Titan taken from behind, showing you sunlight shining through the atmosphere here. Sunlight literally getting bent by the atmosphere and coming around the other side. We've actually landed a robot on the surface of Titan, and this is what the surface of Titan looks like. This was a probe called the Huygens probe that was launched with the Cassini mission to Saturn. And Huygens parachuted down through the atmosphere of Titan and landed on the surface and took a photograph of these things that look like rocks, but are in fact probably solid chunks of ice. Now, an interesting thing about the giant planets, Jupiter, Saturn, Uranus, and Neptune, they have now grown so large from drawing in so much hydrogen and helium that even if we made them significantly hotter, they could still hold on to that hydrogen and helium. And that's important because in many extrasolar systems, solar planetary systems, we see these are planets that are going around other stars. Many of those planets are gas giant planets like Jupiter and Saturn and Uranus and Neptune, but they are much, much closer to their parent stars than our gas giant planets are. And they're much, much hotter than our gas giant planets. But you will notice that even Saturn, if we brought it well into the solar system and it was much, much hotter than it is today, it would still be able to retain its atmosphere. And Jupiter would definitely be able to retain its atmosphere well into the inner solar system. Even if Jupiter were at a temperature of thousands of degrees, it could hold on to its atmosphere. All right. So, where do the atmospheres come from? How do the planets get their atmospheres? Well, the first group of planets I want to talk about are the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. They accumulated their atmospheres. That is, you'll remember early on, they started with rocky, icy cores. And because they grew beyond the ice line in the solar system, they grew out in the part of the solar system where there was lots of ice, they were able to grow very quickly. Because they grew very quickly, they were then able to bulk up, they had a lot of gravity, and they were able to start pulling in hydrogen and helium gas. And as they pulled in this hydrogen and helium gas, their mass got more, their gravity got greater, and they were able to pull in even more and more hydrogen and helium gas. So they were massive enough that they were actually able to pull hydrogen and helium gas out of the protosolar nebula. As a result, today, they consist primarily of hydrogen and helium gas. Those are the dominant components of the outer planets. They started as those rocky, icy cores, but now hydrogen and helium make up the bulk of the planets. In the inner solar system, where the Earth was, we never really had a chance for holding on to our hydrogen and helium. We were close enough to the sun that we were always too warm to bulk up and hold on to this hydrogen and helium. For Earth to have developed a substantial hydrogen-helium atmosphere, the Earth would have to have been significantly farther out in the solar system, out there beyond the orbit of Saturn, say, out there where Uranus and Neptune are. Then the Earth would have stood a chance at bringing in and holding on to a hydrogen and helium atmosphere. But here in the inner solar system, that just wouldn't happen. It was much too hot here. Okay. Well, where did our atmosphere come from? Hydrogen and helium are conspicuously absent from the Earth's atmosphere. And as I said, given the temperature of the Earth, these atoms are just moving too fast. If we add them to the atmosphere today, they can escape. Because the Earth was always in the inner part of the solar system, because it was always warm, the Earth never had a chance to hold on to hydrogen or helium. And that's why the Jovian planets are able to hold on to it. When we look at the Earth's atmosphere, we also notice that there are some noble gases that are missing from our atmosphere. These are gases that are actually very common in the sun and very common in the gas that surrounded the sun when the planets were forming. And these noble gases are krypton and xenon and neon. And what that means is that our current atmosphere does not derive from the original solar nebula. So, the abundance of these elements is significantly lower than what we find in the rest of the solar system, in the giant planets and in the sun. And this implies that our current atmosphere is not the original atmosphere, or that the original atmosphere was substantially weaker than our current one. So where does it come from? Where did our atmosphere come from? And actually, before I talk about that, I will say that the smaller terrestrial planets, so all of the Mercury, Venus, Mars, and the Jovian satellites were not massive enough to retain any gas from the protosolar disk. So none of the moons of Jupiter and none of the terrestrial planets were massive enough to retain that gas from the protosolar nebula, including the Earth. So where did we get our atmosphere from? We got our atmosphere and our oceans, it turns out, from two places: gases released in volcanic eruptions and direct delivery by cometary impact. So the first thing to know is that when a volcano erupts, it releases a tremendous amount of gas from deep inside the Earth into the Earth's atmosphere. And the gases that it releases are water vapor, carbon dioxide, and nitrogen gas. And these are gases that are baked out of the rocks deep underground. Another major source of gases in our atmosphere and water on Earth come from asteroids and comets bombarding the Earth. As comets hit the Earth, comets are cold, icy bodies, primarily made of water ice with other ices like methane and ammonia. And when they hit the Earth or burn up in the atmosphere, all of that water vapor gets returned or gets deposited on the Earth. So let's look at volcanoes here for a second. This is Mount Etna erupting in Italy. And two things that you see here. The first thing you will see is this very dark brown cloud. And those are actually little particles of rock and dust. As Mount Etna is erupting, it is throwing large amounts of dust into the atmosphere. But the white fluffy clouds that you can see here, those white fluffy clouds are primarily gases and water vapor. Mount Etna is not only releasing tiny particles of rock and dust, but it's releasing water vapor, carbon dioxide, and nitrogen into our atmosphere. Another example of this is the explosive eruption of Mount St. Helens in May of 1980. Released tremendous amounts of water vapor into the atmosphere. So much of the water vapor on Earth was originally located deep underground, and it was in the rocks. It was part of the rocks. It was chemically bound to the rocks, or it was just in the matrix of the rocks. And as those rocks are heated and brought close to the surface, the water vapor can escape from the rocks and escape into the atmosphere, and eventually it will condense and fall into the oceans as water. Another possible source are comets. As I've mentioned, comets are cold, icy bodies, primarily made of water ice, frozen carbon dioxide, frozen carbon monoxide, frozen ammonia, frozen methane, but mostly water ice. And as these comets come close to the sun heats up the icy body. The water sublimates, which means it goes from a solid to a gas, and the solar wind blows it in this beautiful tail. Now, comets also contain little tiny particles of rock and dust, and the rock and dust get blown away from the sun, and they make this beautiful yellowish white tail that gets its color simply from reflected sunlight. Those tiny particles of rock and dust reflect the sun's light, so they glow yellow in color. The water molecules, the carbon dioxide molecules, the carbon monoxide molecules, they are so small and lightweight that they get blown directly away from the sun in a beautiful blue ion tail. And these are the gases that were released by the comet. Well, should a comet like this strike the Earth, all of that water vapor, that carbon dioxide, carbon monoxide, the nitrogen ices, the ammonia ices, they all become part of the Earth. And we see lots and lots of evidence in the solar system for cometary impacts. This is Jupiter's large moon Ganymede, and there's a fantastic chain of craters on Ganymede. The odds of a dozen different asteroids or comets striking this moon in a perfectly straight line are infinitesimally small. That's not what happened. What happened here was a comet. Comets are very loosely held together. A comet probably passed too close to Jupiter. And as it passed by Jupiter, it got pulled apart into a string of smaller cometary bodies. And those bodies then struck Ganymede almost immediately after the comet was broken apart, so that they made this beautiful line of craters like that. The origins for our oceans are very similar to the origins of our atmosphere. So the ocean, the water in our oceans, probably came both from volcanic activity, the release of water vapor by volcanoes, and also from the release of ices by cometary impacts. Now, the release of water vapor by volcanoes has been going on for the whole history of the Earth. From the very beginning of the history of the planet Earth. And presumably when the Earth was much hotter early on, there was much more volcanism, which would have released more water vapor into the atmosphere than what we see today. And it is definitely possible that all the oceans on Earth today were released by volcanoes, by released water vapor released from inside the Earth. And as I've already mentioned, it is also possible that the oceans, or at least some of the oceans, came from bombardment. Now, this bombardment of comets and asteroids was more common in the early solar system. We will see later on in the course that there was a very violent period, just after the formation of the solar system, called the early heavy bombardment, when the solar system was being cleared out, and lots of those bodies were striking the Earth. And those impactors are either rock or ice. The rocky ones we call asteroids, the icy ones we call comets, but even if only a small percentage of them were cometary icy bodies, they could have supplied all the water in the Earth's oceans. Ultimately, it turns out that probably both bombardment and volcanoes contributed significantly to our atmospheres and oceans. But we can actually use the ratios of various isotopes, oxygen in particular, but hydrogen and others. Isotopes are elements that have the same atomic number, but a different atomic mass. So, for example, a hydrogen atom has an atomic mass of 1, but the isotope deuterium has an atomic mass of 2. And when we look at the ratios of deuterium to hydrogen on the Earth and in comets, it appears that probably less than 50% of the Earth's oceans came from comets. If more than 50% of the Earth's oceans had come from comets, the ratio of deuterium to hydrogen would be different in our oceans. It would be a better match to comets, and it is not. So it is likely that most of the oceans came from volcanic eruptions. So let's move on to a different question here, actually a really interesting one. We've got 2 planets in our solar system that are almost identical to one another, Venus and Earth. Venus and Earth are about the same size. They have the same surface gravity. And truthfully, they're not that far apart in the solar system. Venus is only a quarter of an astronomical unit closer to the sun than we are. So why are Venus and Earth so different from one another? Why are they so tremendously different? Venus has a tremendously thick atmosphere. That thick atmosphere has a huge greenhouse effect, which means that, well, we'll see this in a minute, that the visible light gets through, but the infrared light cannot get out. That ultimately makes Venus the hottest planet in the solar system. Its atmosphere is 90 times the atmospheric pressure on Earth. It's much too hot to have liquid water. How did these planets end up so dramatically different from one another when, for the most part, they're the same size, they have the same gravity, they have the same composition, and they're not that far apart in the solar system? The answer to why these 2 planets are so different from one another has to do with the fact that there is liquid water on the Earth. Liquid water is what removed the carbon dioxide out of the Earth's atmosphere. Early in the solar system, the Earth probably had a very, very thick atmosphere, just like Venus did. But the Earth was just far enough away from the sun that liquid water could exist. And it turns out that carbon dioxide dissolves really well in liquid water. And if you don't believe me, let me show you this little video here to show you that carbon dioxide dissolves really well in liquid water.
Tap 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 no. Tap 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 no. Tap 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 no. Tap 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 no. Tap 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 no. Tap 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 no. Tap 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 no. Tap 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 no.
So briefly, let me describe what's going on. They've got bottles of Diet Coke here, and I'm sure that many of you, probably in high school, you had a science teacher that did the Diet Coke and Mentos experiment. So what's going on in this experiment? Well, you take a Diet Coke, and you take the lid of the Diet Coke, and you remove the lid, and you drill a small hole in it. And then you drop a Mentos inside the Diet Coke. Better yet, what you do is you mount the Mentos. Mentos, by the way, for those that aren't familiar with them, they're little candies. And you mount them on the inside of the lid, and you screw the lid back on, and you come up with some mechanism to release them into the bottle of Diet Coke. What happens is there is a tremendous amount of carbon dioxide dissolved in the water that makes up Diet Coke. And when you drop those Mentos candies in there, those Mentos candies provide what's called a nucleation site. The carbon dioxide can come out of solution and can nucleate on the surfaces of the Mentos. Well, once all that carbon dioxide starts gathering on the surface of the Mentos, it forms bubbles. Those bubbles are less dense than the water, so they rise quickly out of the water. And in fact, so many of them are generated and they rise so quickly that they spout out the top of the bottle, carrying a large amount of the water and Diet Coke with them, and creating the sort of explosions that you see in the Diet Coke and Mentos experiment. I'll let you go on YouTube and you can watch the rest of that video when you get the chance. It's really a fun video to watch them releasing all that carbon dioxide. But more seriously, let's talk about why the Earth and Venus are so different. The Earth was just cool enough in the early solar system to have liquid water on the surface, and carbon dioxide dissolves in liquid water. Now, what happens is when the carbon dioxide is dissolved in the oceans, life and other chemical processes, but primarily life on Earth, takes that carbon dioxide out of the water, combines it with calcium and other elements, and makes carbonate rocks. Now, what they make is I shouldn't say they make carbonate rocks. They make shells for themselves, right? They make calcium carbonate shells. When those animals die, those shells fall to the bottom of the ocean, and those shells build up over time. And eventually they build up so thickly on the bottom of the oceans that they form huge beds of limestone. Limestone rocks, which is very common here in Virginia, limestone is calcium carbonate rocks. And those rocks came from the shells of animals that lived hundreds of millions of years ago. Those animals removed carbon dioxide from the atmosphere. So like Venus, the Earth probably began with a massive carbon dioxide atmosphere, probably 100 times the mass of our current atmosphere. But over time, virtually all of this carbon dioxide was dissolved in the oceans and was deposited as carbonate rocks on the Earth. If we could take all the carbonate rocks on Earth today, take all of the limestone on Earth today, and bake it at very, very high temperatures, it would release the carbon dioxide, and we would end up with an atmosphere that is the same thickness as Venus's atmosphere today. Now, once all the carbon dioxide was removed from our atmosphere, the next most abundant element was nitrogen, and that is why nitrogen is the primary the thing that makes up most of our atmosphere today. Constituent, that was the word I was looking for. It's the primary constituent of our atmosphere today. That raises an interesting question. Where does molecular oxygen come from? Volcanoes do not emit molecular oxygen, and the reason for that is molecular oxygen, O2, is highly corrosive. It'll very quickly react with any kind of metal to oxidize or rust the metal. Most of the oxygen is on planets like Venus and others are locked into other molecules, such as carbon dioxide. Here on Earth, life is what produces oxygen. Specifically, plants consume carbon dioxide, and for the most part on the Earth, it is primarily single-celled organisms like algae consume carbon dioxide, and they release oxygen via photosynthesis. We all thank trees for doing this as well, but in terms of biomass, there's much more algae in the world that is doing this than there are trees in the world doing this. And in fact, the early atmosphere on Earth became oxygenated thanks to algae, single-celled algae that were converting carbon dioxide into oxygen. I think in the future, humans will be able to tell whether a distant planet has life on it or not, and they can tell if there is oxygen in the atmosphere. Oxygen is such a highly corrosive gas that it won't last long in a planetary atmosphere. If you release oxygen into a planetary atmosphere in a very short period of time, it corrosively will combine with the metals in the soil and with other materials in the soil, and it will disappear out of the atmosphere. So if you find a distant planet and see molecular oxygen in the atmosphere, that molecular oxygen has to be constantly replaced, and that means that that planet has life. Here on Earth, the first oxidized rocks were found in geologic strata that are about 1.2 billion years, date back to about 1.2 billion years ago. So that's very recently compared to the 4.6 billion year age of the Earth. So for most of the Earth's history, the Earth did not have a significant amount of oxygen in its atmosphere. About 600 million years ago, oxygen constituted about 1% of the atmosphere. And biological activity has increased that amount of oxygen to the 21% that we have today. And that is what makes animals possible. Animals on Earth, you and me and all the other animals, we could not survive without that oxygen in the atmosphere. Because unlike plants, we don't make our own energy, and we need the oxygen from the atmosphere to combine with the carbon that we eat to generate the energy that we need. So we consume oxygen to derive energy, and it is plant activity that makes animals possible. Now, I mentioned that Venus is incredibly hot, and I just want to spend a moment here talking about the greenhouse effect. The greenhouse effect is important. Here on Earth, the equilibrium temperature of the Earth would be significantly colder if it weren't for the fact that our atmosphere traps heat down on the surface. So our Earth is as warm as it is, in part because of the greenhouse effect. Venus is the hottest planet in the solar system because it has what we term a runaway greenhouse effect. What happens in the greenhouse effect is visible light, which has a short wavelength, can get through the atmosphere. It warms up the surface, and then that warm surface emits infrared light. Well, infrared light is preferentially absorbed by certain molecules in a planetary atmosphere. And those molecules that are very good absorbers of infrared light are water vapor, methane, and carbon dioxide. Those are probably the three primary greenhouse gases here on the surface of the Earth. Now, what's happened on Venus with its very, very thick carbon dioxide atmosphere is the sunlight could get through, the surface could get quite warm, and as the surface tried to cool itself off by emitting infrared light, all that infrared light was absorbed by the atmosphere and it couldn't get out. So Venus has slowly heated up over time. Now it has reached an equilibrium. Now the surface is so hot and it's emitting so much infrared light that the amount of energy coming in from visible light is balanced by the amount of infrared light escaping. But that's only possible because Venus is very, very hot. The Earth, on the other hand, has a much smaller greenhouse effect. The visible light makes it down to the surface. It warms up the surface. A lot of the infrared light is able to escape. Some of it is trapped by the greenhouse gases, water vapor, carbon dioxide, methane in the atmosphere. And as you're probably familiar, scientists are significantly concerned about the fact that humans are adding significant amounts of carbon dioxide, a greenhouse gas, to our atmosphere. And that carbon dioxide will trap more of this infrared light, which will cause the Earth to warm. As the Earth warms, we are likely to release more carbon dioxide, which will cause the Earth to warm even further. Now, we're not immediately worried about a runaway greenhouse effect, but over the long term, we have to be concerned about a planet like Venus. In the case of Venus, what probably happened early on is Venus may have had liquid water on its surface in the early days, but because it was just close enough to the sun, and the greenhouse effect was just effective enough, Venus warmed up very quickly that all that water vapor was evaporated in the atmosphere. And remember, water vapor is a good absorber of infrared light. So as you add lots of water vapor to the atmosphere will warm up even more. And eventually it will get hot enough that water can no longer precipitate and fall from the skies as rain. That would be defined as a runaway greenhouse effect, where you now start adding so much gas to the atmosphere, so many greenhouse gases, that the Earth starts warming up, and that starts releasing more greenhouse gases, which warms it up further, releases more greenhouse gases, which warms it up further, and it will keep running away, and it will continue nonstop until the Earth is not habitable. All right, finally, let's talk about why the sky is blue. So our atmosphere is probably most famous, at least in our everyday lives, for being the beautiful blue color that it is. Why is our atmosphere blue? The blue light in our atmosphere comes about because molecules in our atmosphere are just the right size to preferentially scatter blue light as opposed to red light. So let's look at what goes on in our atmosphere. Red light and blue light are coming down from the sky and making it down to the deep down into the atmosphere. Red light has a much longer wavelength, and red light typically makes it through the atmosphere without scattering. But blue light has a much shorter wavelength, and those shorter waves are more easily scattered by the molecules in our atmosphere. And what that means is, imagine that I'm standing here. The sun is up here in the sky. But when I look over here, I see blue sky. And I see blue sky because blue light from the sun came in and scattered off a molecule, and that molecule was scattered into that blue light was scattered into my eyes. And when I look over here, I see blue sky, and I see blue sky because blue light from the sun hit a molecule and it scattered into my eye. So we get white light from the sun, but the sky appears blue because the red light from the sun makes it through, but the blue light from the sun hits molecules in the atmosphere and scatters into our eyes. This also explains why sunsets on Earth are very red. Sunsets are red because when you're looking straight overhead, you're looking through about 100 kilometers of atmosphere. But as you look lower and lower in the sky, you are looking through more and more atmosphere. Eventually, you're looking through so much atmosphere at the times of sunrise and sunset that almost all the blue light is scattered away, and only the red light from the sun gets to us. The same is true with the moon. You may have seen an evening where the moon rises and it's almost red in color, or certainly orange in color. That has nothing at all to do with the moon. The moon is white. It's just reflecting sunlight. What's happening there is the light from the moon, as it passes through the Earth's atmosphere, all the blue light is getting removed because it's getting scattered away, but the red light makes it through. All right, so now let's talk about Venus and Mars. The atmosphere on Venus, Venus's atmosphere, is primarily carbon dioxide. It's 96% carbon dioxide, and its atmospheric pressure is 90 times the atmospheric pressure of Earth's atmosphere. Now, to put that in perspective, that's equivalent to the pressure about 1,000 meters, which is 3,000 feet below the surface of the ocean. That is deeper than U.S. nuclear submarines can go. A typical U.S. nuclear submarine has a crush depth of about 750 meters. The actual crush depth is classified, but probably right around 750 meters is the limit as to how deep U.S. nuclear submarines can go, which means if we took a new U.S. nuclear submarine and placed it on the atmosphere of Venus, the atmospheric pressure alone is enough to crush it. Just the gas alone could crush a submarine. What's the color of the sky on Venus? So on this learning catalytics question, the atmospheric pressure on the surface of Venus is 90 times the atmospheric pressure on Earth. What is the color of the sky on Venus? Go ahead and take a moment to answer this question in learning catalytics. All right, welcome back. What do you think on this one? Well, you might remember the images that I showed you. On Venus, the atmosphere is so thick that long before you get to the ground, all the blue light is scattered away. And the only thing that's left by the time you get close to the surface is red light. And the atmosphere on Venus is so thick that even the red light can get scattered. And so when you're standing on the surface of Venus, it is much dimmer than on the surface of the Earth, and it is much redder than on the surface of the Earth. And that's because little sunlight, or less sunlight, I should say, makes it down to the surface. And the only sunlight that makes it down to the surface is the deep red light. All the blue light is scattered away. Mars has an atmosphere that is on the opposite end of the spectrum from the Earth's and from Venus's atmosphere. Unlike Venus, which has a very thick atmosphere, Mars has a very thin atmosphere. It's only 0.007 times the atmosphere of the Earth, or 0.7% the Earth's atmosphere. That's equivalent to an altitude on Earth of 110,000 feet. And the Martian atmosphere is primarily 95% carbon dioxide. So just like Venus, the Martian atmosphere is mostly carbon dioxide. But what this means, a carbon dioxide atmosphere that's very, very thin, is that astronauts working and living on the surface of Mars will absolutely require spacesuits. Astronauts will not be able to venture outside their habitat on Mars without a spacesuit on. They'll absolutely need spacesuits. And this is a picture taken, a selfie actually, of the Mars Curiosity rover taken on the surface of Mars. That is Mount Sharp in the background. That is the mountain that Curiosity is currently climbing up the flanks of that mountain. And if you look at the Martian sky in the background, you'll notice it has this pinkish red color. And that comes from the fact that on Mars, the winds blow enough that they levitate a lot of dust into the atmosphere. So what we're not seeing here is scattering by molecules in the atmosphere. We're actually seeing little tiny particles of red dust, the red dust from the surface of Mars suspended in the atmosphere. And as the sunlight hits those little red particles, they reflect mostly red light, just like the ground reflects red light. And that's why the Martian atmosphere has this pinkish red color. Now that we've studied the atmospheres in our solar system, let's take a close look at the Earth's moon. Because the Earth's moon is a fossil. It records billions of years of history. So we'll begin by looking at the single most important geologic process on the surface of the moon, and that's impact cratering. And then we will go on to talk about the history of the moon. So join me in the next lecture when we talk about impact cratering, and we'll use the moon as an example.